Good afternoon, folks. I hope everybody is doing okay right now. This is my final lesson in my History of Science sequence for this semester, dealing with science in the 20th century. If you are a student in my History of Science course, you should probably go online before you get much further and get a copy of the summary lecture notes with the names and the dates when everybody was alive, so that you have that for reference both during and after. Now, we have come at last to the 20th century, which in many ways I would have to characterize as the golden age of science. More progress is going to be made every single decade of the 20th century in terms of scientific discovery than in the entire history of science prior, including the previous decade of the 20th century. Our growth in knowledge, both applied and theoretical, is going to be exponential. The 20th century is going to be a period that's going to see science fully blossoming into the modern form that you know now. This is going to be a scientific world in which anybody who's taken seriously has a degree in the sciences. Anybody who's doing their own self-directed research probably has an advanced degree. Most scientific work is sponsored by either governments, universities, or by private enterprises. There's a lot of industrial research, a lot of applied research for everything from engineering firms to pharmaceutical companies. A lot of research is going to be done in the biomedical industries. A lot of research is going to be sponsored by government agencies, whether that means organizations like the National Wildlife Federation or the NOAA or NASA, or whether that means organizations like DARPA doing research for military applications. We're going to find that academia is the home to a lot of theoretical research, that it's common to be the professor academic who does research as part of your scholarly duties, a model that no doubt many of you hearing this are well familiar with and will be living yourselves. You might note that conspicuously absent from that list is the gentleman scientist. The age of the private research laboratory in your own house is pretty much a thing of the past. We are not going to be seeing significant, serious scientific research done by amateurs anymore. You will get the occasional little moments where an oddity happens. Famously, of course, Steve Jobs and Steve Wozniak put together the first personal computers in a garage. You're going to get the occasional astronomy discovery made by an amateur with a good telescope. But for the most part, science has become a strictly professional endeavor. And those odd situations where someone who's a basic amateur or hobbyist manages to make a significant contribution are becoming a thing of the past. Scientific publications proliferate, journals and books of all sorts, hundreds, if not thousands, of different journals on specialties and subspecialties in countries all over the world. Conferences, both national and international, dealing with broad topics or specific ones, are major sites for scientific endeavors. Scientific societies remain a thing, but they're not even the primary venue where scientific knowledge is disseminated anymore, largely becoming in some ways sort of an honorific more than anything else. Scientific enterprise has become established in day-to-day life. And I think maybe more than anything else, that is the key to understanding science in the 20th century, that by this time, science has become the default paradigm. We have gone from a world at the beginning of this course in which there was no distinction between science and magic to a world in which now we are seeing science is the basic standby by which most people view the lens of the world. This is not to say that the average person is a scientist or even necessarily knows all that much science, but it does mean that the average person acknowledges and understands the existence of scientific explanations for natural phenomena, that most people are going to look to saying, okay, well, why do the birds fly south for the winter, and look for an answer that says it's because of a change in meteorologic phenomena or because of an instinct of some kind, as opposed to, an unseen deity whispering in their ears and telling them that the cold is coming. That basically the paradigm of magic, the supernatural, and a paradigm primarily informed by religion or spirituality has taken a back seat in the overarching societal view of how things work. Again, this is not to say that religion has gone away. It is not to say that belief in magic has gone away. But what it does mean is that the starting point for most people's consideration of how to explain natural phenomena is the scientific method and the knowledge that has been accumulated by scientists over the centuries. The world that we live in the 20th century is one that is made possible by scientific progress. Industries driven by machinery, powered by scientific discovery, electricity flowing into our homes along lines from generators, driven by the work of people like Faraday and Maxwell. We've got medicine largely being done through the lens of empirical and laboratory-based investigation as opposed to humorism and treatments taught by the village doctor. Science is embedded in every aspect of 20th century life, and that is going to be a prevailing theme of what happens in the 20th century. It is no longer possible to envision a world without science in it, in which science is not one of the driving forces of virtually every kind of progress. Scientists are well established in society and generally respected individuals, even if they're not necessarily always the best paid individuals, depending on, what kind of branch of science you're doing. Now, I am not going to pretend that it is even remotely possible to describe everything going on in the science of the 20th century in one lesson, or indeed even in one course. There is simply too much happening. So what I've endeavored to do for this lesson is to kind of give you a greatest hits, if you will, to take a look at some of the primary scientific achievements, primarily of the first half of the 20th century, going about as far as the beginning of or the space age. So we're going to terminate our discussions probably right around the late 60s, early 70s. This is partly because I need to limit it somehow, and partly because anything from that point onward is quite frankly within living memory. That if we're looking at science from, say, the 1970s onward, the folks who are doing that work probably remember it, are probably alive for it, and we have not really had the lens of a significant number of generations to look back on and judge the impact at a historical perspective. Now, this is not to say there is not science history done of the 1970s, 80s, and 90s, but it is to say that anything more recent than the 1960s is something you can reasonably expect that people who are still working in the sciences are firsthand familiar with. At least some of those folks are. Obviously, a lot of those folks who were doing their primary work in the 70s are probably at this point in the twilight of their careers, but nonetheless, they were there for it. They did that work. They were contributing to it. It's part of the current, if you will, corpus of inherited knowledge in the generations that are still alive and still doing science now. So I've chosen that as a delimiting point to really kind of box in what we look at. Now, as we are progressing, I want you to keep two big things in mind. One, we are talking about the science of the 20th century, more so than any other time in history. It is a collaborative affair. Science is the work not of individual geniuses for the most part, but of teams, of groups of people working together on solving collective problems. A lot of cases, that means groups of students, groups of assistants, groups of technicians, working with 1 or 2 or 10 scientists who are all contributing to a big idea. Look at any scientific publication, and the list of authors is half a page long. That's become the norm rather than the exception. So I want you to keep in mind that although I am continuing to take the broadly biographical approach to looking at science that has characterized most of this course, I do want you to remember that for every name that I mention, there are dozens that I'm not. Partly because there are too many names to mention, partly because a lot of those folks were working quietly in the background, and it's important that we remember that they were doing what they were doing. Secondly, I want you to keep in mind that a lot of science in the 20th century is being driven by the needs of governments, and specifically by the needs of militaries. We are going to see the 20th century become a time when scientific and military progress become inextricably intertwined. World War I is arguably the first science war, the first war in which who had the best science was a significant driving factor in who won and who lost. We're going to find that this means that we are in a place where, what are the tools of World War I? Think about your World War I. What do you envision? You envision machine guns. You envision gas. You envision airplanes. These are all technologies that were very new at the time. You had the German chemist Fritz Haber, who was noted for developing the fertilization techniques that have been used by agriculture up to the present day, have produced food that can feed billions of people. One of the great heroes of human society in terms of feeding people was also the inventor of chemical gas weapons. And that particular conflict in his legacy is one that even he himself never fully resolved. You're going to have the Wright brothers having developed their first aircraft that successfully got off the ground in the early 1900s. Just a decade later, people are flying aircraft that can drop bombs. And we're finding that the medical advances of a society that is beginning to formally train physicians and surgeons at a university level are keeping thousands, if not millions, of soldiers alive who otherwise would have died on the battlefield. So yeah, science has changed the way that we even make war. And because of that very fact, governments are going to be investing in it heavily, if for no other purpose than for military application. One of the big themes that's going to be covering a lot of this class, especially since we're looking at the first half of the 20th century, is going to be the close relationship between science and the world wars, in particular World War II, which is going to prove to be the catalyst for a significant amount of scientific development for good and for ill. So, science and government, science and war, these are prominent themes that are going to be defining everything we do in this lesson. So, how do we narrow it down? It's really, really hard to bring focus to all of this. It's really hard to decide what is and isn't important to include. And I am necessarily going to be having to leave out a lot of scientists and a lot of people and stories that are really cool and really fun and really important. There are too many important stories for me to even tell all of them. I'm probably not going to tell you a lot about Rita Levi Montalcini, the rather amazing Italian scientist who did her research secretly in sheds while she was on the run from the Axis powers during World War II and developed nerve growth factor. I'm probably not going to be telling you about Louis Leakey, who was the paleoanthropologist in Kenya and Tanzania, who finally proved Darwin's prediction that the first humans came from Africa. I'm probably not going to be telling you about names that you might have heard in the course of your scientific research or studies. We're not going to be talking a whole lot in here about Rachel Carson, the great environmental scientist. We're not going to be saying a lot about Barbara McClintock, the geneticist. We're not going to be saying a lot about Mitchell Feigenbaum, the chaos theorist. We are not going to be saying a lot about Richard Feynman, one of the great minds of the atomic era. There are too many scientists in too many disciplines for me to even begin to scratch the surface of all the good ones. So what I have done is I have put together this lesson with an eye towards hitting the major theoretical developments of 20th century science, the really big, powerful things that we cannot ignore, the things like quantum mechanics, nuclear power, space exploration, DNA, and so forth, trying to hit all of the major domains of science with at least one of their big theoretical accomplishments. 2, I have looked at putting this lesson together with an eye towards the best stories, with looking at the people and accomplishments that are the most interesting, the most engaging, the most human, the ones that we can really tie into our understanding of the world that we live in, the ones where we have people with big personalities doing big things, the ones that really moved and shook our world. And a lot of these stories are very dramatic. Science in the 20th century, as in every century that we've discussed, is the work of passionate people dedicated to knowledge. And we have the luxury, being so close to this time period, of knowing more about their lives and the intimate details of them than any other time in history prior to this. A lot of the scientists I'm going to tell you about today did their work within living memory, that there are folks alive today who worked with them and knew them. Some of the folks I'm going to tell you about today are still alive, at least one anyway. So this is a period of science history in which we have the unusual luxury of a large amount of very personal biographical data on these people. We know their faces, we know their voices, we have papers written in their own hands, we have accounts of people who knew them and worked with them. And therefore, we have the ability to tell some really dynamic and amazing stories about them. So, I may not hit your favorite scientist today, but I'm going to try to tell you some stories that I think at least are pretty cool. So I thought long and hard about where was the best place to begin talking about the science of the 20th century. And I decided to begin with one of its more, to my thinking, colorful and, until fairly recently, not acknowledged characters. Someone who has undergone a bit of a renaissance in the internet age, has become a bit more of a well-known figure, and hopefully you know his name already going in. I have not spent a lot of time in this class on inventors. Most of our attention has been to the theoreticians, the people who did the work of working out the principles in science, and therefore building the corpus of ideas that inventions were made from. The figure I want to begin with is a man who, although he did some important theoretical work, is primarily remembered for his inventions, for his use of applied science to devise technologies that every last one of you is using at this exact moment. I'm referring to one of the 20th century's greatest inventors, indeed one of the greatest inventors in any century, a Serbo-Croatian physicist and electrical engineer by the name of Nikola Tesla. Nikola, N-I-K-O-L-A, Tesla, T-E-S-L-A. Tesla was born in 1856, died in 1943, and I do not think it would be too much of a stretch to say that Nikola Tesla invented the 20th century. His creations impacted every aspect of the life that you're living right now, and you don't pass a day without using things that Tesla created. Now, Tesla's life was dramatic from the beginning. He was born at the stroke of midnight during a thunderstorm between the 10th and 11th of July, 1856. His father was a Serbian Orthodox priest. His mother was, to his thinking, the most intelligent individual he had ever met. He said that later in his life, and coming from him, that's saying something. Who was always inventing little gadgets to help out around the family farmhouse. He was a native of what was then the Austro-Hungarian Empire, today living in the nation of Croatia, although he was ethnically Serbian. Tesla, like so many of our great scientists that we remember in here, was a child prodigy. By the time he was 10 years old, he spoke 8 languages fluently and could do integral calculus in his head. So much so that his village school teachers thought he was cheating and presented him with problems to solve on the spot to prove that he actually had the abilities he claimed, and, well, he did. Tesla was a remarkable individual. His mind is one of those rare minds that is almost impossible to comprehend. He had a photographic memory. He could recite from memory virtually everything he had ever read, ever seen. He said that the images were just like a filing cabinet in his mind that he could pull up at will. One of his favorite party tricks is that people would say to him, okay, Tesla, Bible, Jacob, chapter 3, verse 16, give it to me in Serbian. And without a moment's hesitation, he would, because he had memorized the Bible and could immediately in his head translate it into all the languages he knew. Tesla only slept for 2 to 3 hours a night. He said that his mind was too restless for him to do anything else. He got a lot of his best work done in the wee hours of the morning when no one else was awake. He was a workaholic, pushed himself for sometimes 20 hours a day, except during thunderstorms, when he would pause, stop everything he was doing, lie down someplace where he could watch the lightning, and recite spontaneous poetry until the storm was over. He claimed his ideas came in flashes of inspiration and claimed that he had visions of flashing colors and lights in his mind throughout his life that would sometimes overtake all of his thoughts, and he would come out of them with inspirations on new ways to build things and to route power. He often said that he didn't bother doing experiments with a lot of his inventions, not hands-on anyway, because he said he would simply build the device in his mind, run the experiment mentally, make the necessary recalibrations when it didn't come out the way he hoped it would, run it again, and keep that going until he had perfected the thing he wanted to build in his head, and then he would build it from memory without the benefit of a blueprint, and it would work. Not a lot of people like him out there. Now, when Tesla was a teenager, his father was hoping that he would follow in his footsteps and become a Serbian Orthodox priest. Tesla wished to become an engineer. His father was not hearing of it. But when he was a teenager, Tesla got a very serious case of cholera. It was expected he was not going to survive. He was lying on what he thought was his deathbed, and his family thought it was his deathbed. And his father was at his bedside holding his hand. And Tesla's father said, "Oh, my son, I would do anything to help you heal." And Tesla said to him, "Perhaps if you let me study engineering, I will get better, father." And his father, thinking his son was dying before him, said, "Well, yes, yes, of course, son, anything that you want." And Tesla got better. And his father, true to his word, allowed him to go to school for engineering. Tesla attended the Polytechnic School, the Austrian Polytechnic at the University of Graz, for electrical engineering. Before he had even finished his undergraduate degree, he had been studying the way in which generators worked. He thought of a better way that you could build an alternating current generator as opposed to the direct current motors that were commonly used in electrical engineering at the time. Tesla realized that with alternating current, you could send more energy more efficiently over a longer distance and do so more cheaply. And when he graduated, he decided, this was where he was going to find his fortune. He did not actually go on to doctoral study. He got into a lot of trouble with gambling. He became a gambling addict and ended up having to leave school for a while. But he did eventually finish his degree in electrical engineering, never finished a doctoral degree, and began building his own alternating current AC induction motors. By the age of 24, he had perfected such a motor, and he began shopping it around to various engineering and technical firms throughout Europe. Nobody was buying. Nobody wanted his technology. And a big part of the reason for that is because just about everybody at that point in time had already been investing in another technology, namely the direct current motors and generators being produced by an American scientist who you all have heard of by the name of Thomas Alva Edison. Edison was born in 1847, died in 1931. He was, of course, the preeminent American inventor of his time, invented, among other things, the phonograph, the first recording technology for sounds, invented the light bulb as we use it today, and made countless improvements to many other technologies. Now, Edison held the basic monopoly on electric power in the United States, and by extension, much of the Western world. The Edison Electrical Company sold its direct current motors and generators all over the US and to many European nations, and was the default way that you got power if you were using electricity in the late 19th century. Now, Tesla realized that his technology was superior to Edison's direct current technology. But because everybody in the European firms had pretty much just laid down a large amount of money investing in Edison's technology, and here comes this young, untested scientist claiming, hey, here's a different way you could do it, not a lot of folks were too open to his ideas. So Tesla got the idea. He's like, you know what? I can't get anybody interested in here, but I know who will appreciate my discovery. Thomas Edison will appreciate my discovery. And so Tesla got himself on a boat to New York City, arrived in New York with $5 in his pocket, and made his way to Menlo Park, New Jersey, where you might know is the location of the laboratories of Thomas Edison. He was sometimes called the Wizard of Menlo Park. And there, Tesla arrived with a letter of introduction from one of his old professors who had known Edison. That letter said, Mr. Edison, I have known two geniuses in my life. One of them is yourself. The other one is the young man handing you this letter. With that letter of introduction in hand, Tesla appeared before Edison in 1884, ready to present to him the design for his alternating current technology. And he made the pitch. And here we come to the tragedy of Nikola Tesla's life, that for all of his brilliance, Tesla was a good-hearted, optimistic person who firmly believed in the goodness and kindness of humankind, and that altruism and the benefit of all would trump greed and pride. That particular flaw in his thinking, unfortunately, held him back on many occasions. And here's where we see it beginning. Because Tesla, fresh-faced, young, with this great idea, 28 years old, appears before Edison, pitches this system that is better than anything that Edison himself has put forward. He thinks Edison will be all about it and will hire him on and start building the better technology. He did not count on the fact that Edison, seeing a much younger man with a better idea, would feel threatened. And Edison said to Tesla, Look, Mr. Tesla, you're clearly a bright young man. You've clearly got a lot going for you. But I've been in this business a lot longer than you. This technology is not going to work at a large scale level. It's just not going to be scaled up industrially. But you clearly have a lot going for you. So here's what I'm going to do for you. I'm going to offer you a job here in my firm. You can work for me doing engineering. I want you to make improvements on my direct current power plants to make the existing technology better, not implementing this new thing, but to make the DC tech more efficient. If you can increase the efficiency of my power plants by 50% within the next 5 years, I will give you $50,000 to do any kind of research that you want to do. That was a princely sum of money in the late 19th century. And Tesla jumped on the opportunity and was hired on by the Edison Electrical Company. What he did not realize was that Edison was sending him up the river. He did not realize that Edison knew damn well that you were not going to get 50% more efficiency out of existing DC technology. This was a way of keeping Tesla busy so that he didn't compete with Edison. So Edison set him to this impossible task. Needless to say, Edison was a little bit surprised when 18 months into the 5 years, Tesla came back to Menlo Park, said, "Hey, I've made your direct current plants 75% more efficient. Can I have my money now?" At that point, Edison said to Tesla, "When you have been an American longer, you will understand our American humor." And he offered Tesla a raise from $18 a week to $25 a week. At that point, Tesla told Edison exactly where he could stick his direct current, and he set out on his own. Tried to make a go of it starting his own company, did not have the business acumen to do it on his own auspices, nor did he have the resources to do so. Supported himself doing odd jobs for a while, even worked as a ditch digger for a time. And then eventually, he finds his way in 1888, having invented a polyphasic AC generator the preceding year. In 1888, he finds his way to my own hometown, to the city of Pittsburgh, where he partners up with a Pittsburgh industrialist by the name of George Westinghouse. You probably know that name, of the Westinghouse Electrical Company. The Westinghouse is looking to get in on the electricity biz and to compete directly with Edison. Westinghouse forms a partnership with Tesla to produce power plants operating on AC rather than DC. Westinghouse purchases Tesla's patents for $60,000 and promises him royalties of $2.50 for every horsepower of electrical capacity that's Westinghouse sold. And thus began what came to be known in the 19th century as the Current Wars, the public relations and scientific conflict in the American public over who was going to deliver power to the United States. This war was fought in boardrooms, in newspapers, and of course in industry and laboratories. The simple fact of the matter was that Tesla had a better product. AC was more efficient and cheaper over longer distances. Edison had the benefit of lots of backers, name recognition, and a well-established infrastructure. Tesla had a rich industrialist backing him up in research and a fresh new idea, one that was, frankly, less expensive. Now, the current wars raged throughout the 1880s and into the 1890s, and ultimately ended up being resolved. Kind of the final blow, you might say, was in 1893. We'll talk about that momentarily. Along the way, Edison got nasty. The war became nasty on both sides, a lot of mudslinging, a lot of low-grade industrial sabotage sorts of things. And Edison, for his part, got desperate and began trying to show off how dangerous AC technology was. Edison invented the electric chair as a way of showing how dangerous AC could be. And he began traveling around the country with an AC-powered platform where he would set it up in a public square, electrocute a dog in front of people, and say, "Do you want your little wife at home cooking with that?" And whenever this didn't work, he began electrocuting bigger and bigger animals, dogs, horses, cows, until eventually, and most famously, he electrocuted an elephant to demonstrate how terrible AC would be. But the public was kind of turned off by Edison's rather nasty approach to the whole thing. And in 1893, Tesla, rather than Edison, won the contract to provide electrical power for the 1893 Chicago World's Fair. And if you're not familiar with the Chicago World's Fair of 1893, I recommend you read about it. It was an amazing event in American history. It was kind of the event that showed that America could compete with the big countries like Britain and France and so forth as a technological and cultural power in its own right, rather than some backwater colony on the other side of the Atlantic. Chicago World's Fair saw the introduction of lots of novel technologies and things, including, among other things, the first public use of alternating currents to light a public area. When the so-called White City, the collection of neo-Greek buildings assembled for the World's Fair, was illuminated by night with Tesla's lighting, people were absolutely enchanted. It was a dramatic demonstration of how efficient and beautiful AC power could be, and really kind of the final blow in the current wars. Edison remained in competition, but ultimately AC won the fight. Every joule of electricity generated in the United States today is generated using AC technologies. Now, while all of this is going on, and by the way, if you're interested in the Chicago World's Fair, I recommend a wonderful book by Eric Larson called The Devil in the White City. Half of the book is about the Chicago World's Fair and all the things that happened at it and went into making it happen. The other half is about the notorious medical serial killer Henry Howard Holmes, H.H. Holmes, who during the Chicago World's Fair and the year or two on either side of it, lured perhaps as many as 200 people into his hotel, which was actually a series of torture chambers and cells that the press later dubbed the Murder Castle. He was arguably America's first and most notorious serial killer, killed at least 30 people, maybe as many as 200. So it's a dramatic story, well worth the reading. Now, as all this is going on, Tesla is continuing his research. He never stops working on things. He holds more patents than anybody in American history with the exception of Edison. Hundreds of patents to his name. But a lot of times, Tesla wouldn't bother to defend his patents. He would invent a thing, he would lose interest in it, and he'd move on to the next thing. He was always working on the next project. So what kind of projects are these? Among other things, in the year 1890, Tesla invents a high voltage device called the Tesla coil, used for amplifying electrical current. It's that big crackly coil-shaped thing that you see in every Frankenstein movie right before the monster comes to life. He used it to study high-frequency energy. Using the Tesla coil, he was able to demonstrate the wireless transmission of high-frequency energy and discovered a whole spectrum of radiation emitted by this thing. Incidentally, he used it to take the first X-ray photograph of his own hand in 1892, 3 years before the German scientist Wilhelm Röntgen, R-O-E-N-T-G-E-N, was going to end up discovering X-rays totally independently of Tesla. The very first Nobel Prize in Physics was awarded to Röntgen for that discovery that Tesla had made 3 years prior. Just yet another example of Tesla getting snubbed by the world at large. Using this technology, among other things, he developed some better understanding of high-frequency radiation. He invented not only X-ray technology, but the first fluorescent lighting. And most remarkably, in 1897, a technology called radio. Prior to that, 1896, Tesla completed the Niagara Falls hydroelectric plant, the first hydroelectric plant in the world. In 1898, of course, we're going to see his remarkable work with radio. So 1897, I guess, is where he really does his radio work, that he discovers his Tesla coil emits a low-frequency form of radiation as well that can be broadcast over very long distances. And that he names radio, and he acquires a patent for radio in 1897, realizing that it can be used to broadcast information over long distances with very low energy. And in fact, over a very wide area, what he called broadcasting. Now, I know what you're thinking. You're thinking to yourself, but Mr. Davis, was not radio invented by the Italian-Irish inventor Guglielmo Marconi? Marconi, M-A-R-C-O-N-I, born in 1874, died in 1937, was a student of Tesla's. He was one of many young scientists who came and worked with Tesla in his laboratories. Now, in 1901, Marconi is going to use radio technology to send the first transatlantic radio signal, allowing real-time communication between Europe and the United States for the first time ever. Another one of Tesla's students tells him about this, and Tesla laughs and says, Marconi is a good man. Let him go. He is using 17 of my patents. Maybe Tesla should have paid a little better attention to what Marconi was up to. Because let's build the story a little bit more. So Tesla's continuing to do his research. Between 1899 and 1900, he moves to Colorado Springs, Colorado, to conduct more high-frequency electrical radiation in the rarefied high-altitude atmosphere. He demonstrates that he can actually make lightning, literally make lightning happen in the sky. To this day, we do not know how he did it because the technology was ultimately broken down when he left Colorado Springs, and he left no blueprints. In fact, he was asked to leave the city whenever his experiments caused a shorting out of the power grid when he made lightning that struck things that it shouldn't have. Taking his high-frequency radiation back to the East Coast, he began working on other ways of using wireless transmission of energy. In 1904, Tesla did a not 1904, I'm getting my timeline off. 1898, Tesla did a famous demonstration at another fair before a wide crowd of the first radio-controlled device, first remote control. He had a little toy boat that was in a pool of water and a handheld radio controller that he could use to make the boat turn and move around as he dictated. That boat, incidentally, carried out pre-programmed series of commands utilizing a circuit also invented by Tesla called the AND gate, which some of you computer folks might know, the basic logical 0-1 on-off circuit that is the basis of all computer programming, also invented by him for this device. Now, the crowd was so amazed with this that Tesla had to pass the remote controller around to let people move the boat for themselves to prove to them that it was in fact a signal being sent from the handheld device to that boat. Some of the folks in attendance at that gathering were from the Department of Defense. And they went to Tesla afterwards, and they're like, Mr. Tesla, we like what you're doing here. You want to come work for us? Tesla was a pacifist. And he laughed, and he said, what you see there, you do not see there a wireless torpedo. You see there the first of a race of robots, mechanical men who will do all the laborious work of the human race and end the need for war. The Department of Defense was not entirely thrilled by this. So, a couple years later, 1904, getting my dates off here. Department of Defense goes to Guglielmo Marconi after his famous radio broadcast and says, hey, we would really like to entertain your technology. We would like to set up listening posts and communication with our allies on the other side of the Atlantic using your radio tech. Can you help us out? And Marconi said, well, I'd love to help you out, guys, but this patent for radio happens to belong to Nikola Tesla. Not so much I can do about that. Hint, hint. Thus it was that in 1904, the United States Patent Office withdrew the patent for radio from Nikola Tesla and gave it to Guglielmo Marconi so that he could begin building military radio technologies that Tesla refused to build. Tesla, unusually for him, fought for his own patent. He actually took it to court, and the United States Supreme Court did eventually, in Tesla versus Marconi, find in his favor in 1943, 3 months after Tesla died. So if you go to the U.S. Patent Office today, the patent for radio is the name of Nikola Tesla, not Marconi. Do not give Marconi credit for that. Now Tesla, undaunted, continues his work. He teams up with the industrialist J.P. Morgan, you might have heard that name, to build a project for wireless transmission of electricity. He begins constructing a tower in New York State called the Wardenclyffe Tower, Wardenclyffe, at the site of Wardenclyffe, New York. The Wardenclyffe Tower is meant to be a device that will allow the wireless broadcasting of electrical energy without wires to transmit it by tapping directly into the Earth's magnetic field to do so. Tesla's proposal for the Wardenclyffe Tower states that it will be the center of, as he puts it, quote, a world system of wireless communication for broadcasting news, music, stock market reports, personal communications, and pictures. That's right, folks. In the early 1900s, Nikola Tesla tried to invent the internet. Now, one day, Tesla's having lunch with J.P. Morgan in 1905, and they're talking about the Wardenclyffe project. And Morgan is super happy with this, and Tesla says, Mr. Morgan, I'm so glad that you're helping me to do this great project for the benefit of humanity. And Morgan, with the dollar signs in his eyes, says, yep, I'm a great humanitarian, I am. And Tesla goes on happily and obliviously saying, and it's wonderful that you're willing to forego so much profit in order to make this device happen. And Morgan says, what the what now? And Tesla, who is still not caught on, happily goes on to tell him that once the tower is up and running, because it will be broadcasting electricity using the Earth's magnetic field itself, anyone with a receiver will be able to get it. And there will be no effective way to charge people for it. Free electricity for everyone. Morgan pulled the plug on the project. He was not going to endorse that. And to Tesla's horror, the Wardenclyffe Tower was later scrapped to make bombs during World War I. We did not figure out how Tesla did wireless transmission of electricity until about 5 years ago. We have finally replicated the technology that he had mastered back then. And it's going to change the world one of these days, once we figure out the best ways to scale it up large scale. Now, Tesla continues his projects despite all of this. He invents bladeless turbines. He invents what he calls the apparatus for aerial transportation, which is the forerunner of the modern vertical short takeoff and landing vehicles, VSTOL, used by the military. He continues making tweaks to his technology. He studies oscillating systems, which he claims, with the right vibrations, can shake apart anything from a building to the planet itself. He experiments with early forms of laser technology. There's a persistent claim that he invented a quote-unquote death ray that could potentially destroy the world if misdeployed. But ultimately, towards the end of his life, he started getting really eccentric. He argued with Albert Einstein about basic principles of relativity. He started claiming the possibility of intelligences in other worlds. There was a cult that began viewing Nikola Tesla as a messiah who had come from the moon in a chariot pulled by swans. And he got a little bit weird towards the end of his life and ultimately died penniless in a New York hotel in 1943, having won and lost several fortunes during his life, mostly while other people got rich off Tesla's patents. When he died, the authorities came into his apartments, seized papers and prototypes. To this day, keeping in mind for a moment here that Tesla has been dead for 77 years, approximately 2/3 of the papers and devices seized by the FBI from his departments in 1943 are still classified. They're still considered too sensitive to release to the public. One of those technologies, a sonic disruptor weapon used to disperse crowds, was actually deployed right here in Pittsburgh a few years ago when we hosted the G20 summit, and there were lots of protesters, and a technology Tesla had proposed in 1928 was finally built in the early 21st century once we finally caught up with his brain. Now, I've told a lot about Tesla already, but before I leave his story behind, I would be remiss if I didn't tell you one other thing about him, that by any reasonable standard, Nikola Tesla was, frankly, a little bit off the wall. He was severely obsessive-compulsive. Whenever he went to a restaurant, he would not order anything that was on the menu. He always ordered a custom order. He refused to have it brought by a waiter because he said that waiters were dirty, and he was intensely germophobic. He had to have it served by the maitre d' himself. He would not eat anything until he had personally polished every plate and every utensil with 17 separate silk napkins. And then he would not take a single bite till he had mentally calculated the cubic contents of every course, because he said without that knowledge he could not properly enjoy the meal. He would not enter a building unless he had walked around it at least 3 times. His germophobia meant that he never touched other people, and he refused to let them touch him. As far as we know, he died a virgin. He could have potentially married J.P. Morgan's daughter, which would have probably been good for his fortunes, except for the fact that he also had an intense fear of spherical objects, and he was frightened of the pearl necklaces that she wore. I think one of the great tragedies of Tesla's life is that his ashes are interred in a spherical urn. That just doesn't seem fair to me. And for all that the dude is a germaphobe, he loved pigeons. He absolutely adored pigeons, and they loved him too. He was good personal friends with Mark Twain, and Mark Twain reported that one day the two of them were taking a walk in New York City, and Tesla just looks up into the sky and puts his hand up and kind of goes, "Wah, wah, wah," and a pigeon just comes down and lands on his hand like he's some kind of garbage barge Snow White, and he gives it kisses, and he pulls out treats that he's carrying in his pockets. The pigeons loved him, and he loved them. When the FBI went into his apartments after his death, they found 14 pigeons that he was nursing back to health from various injuries and illnesses. My absolute favorite story about Tesla was that in 1916, he received an award for his lifelong contributions to electrical science. Ironically enough, it was the Edison Award, but what can you do? And so comes time for the keynote speech, and he's supposed to be giving a talk, and they can't find him. And they're like, okay, well, he's probably out walking in circles around the building or something. So they sent people into the surrounding streets looking for him. They found Tesla in a park across the street, arms outstretched like St. Francis of Assisi, pigeons all over him as he threw back his head and laughed at the sky. There's a picture of that. It's one of my favorite pictures I have ever seen. You can look it up on the internet. Okay, but I spent far longer on Nikola Tesla than I wanted to. No, I didn't. I love talking about Tesla. I hope you can see why. And if anybody wants to know more about him, he's one of my favorite people in all the history of science. There's a wonderful biography of him called Tesla, Man Out of Time by Margaret Cheney. Well worth your time to read. All right, though. So Tesla is a guy who only recently started enjoying some recognition for his rather amazing career. But he's hardly the only cool scientist in the 20th century. Let's talk about a 20th century scientist with an equally amazing mind who you have all heard of, who has always gotten the recognition that was right and due to him. Let's talk about good old Albert Einstein. Einstein was born in 1879, died in 1955. We're just a couple days off the anniversary of his death, April 18th. He was a Swiss-born physicist, although at various points in his life, he held German, Swiss, American, and Israeli citizenship. Which I say Swiss-born, he was German-born. My bad. Tesla was a native. Sorry, Tesla. Damn it. Okay. So Einstein was a native of Germany. His father was a salesman who did some engineering and got him interested in the science as a young boy. Einstein reported that his father gave him a compass when he was just 6 years old, and he was fascinated by how the compass needle would always revolve to point its way to the north. And he claimed that gift inspired him to want to pursue a life of science to understand how such forces would work. You have no doubt all heard that Einstein was a terrible student, that he failed mathematics in school. We often cite that as an inspirational story that, guy who failed math when he was in school, look what he could rise to achieve. That is completely not true. Einstein did very well in school. He was a gifted mathematician from the time he was a young age, but his grades were poor, largely because he didn't focus on the things he was supposed to be doing. He was interested in personal study of mathematics, outside reading on topics of interest to him, and playing the violin, and therefore ignored a lot of the standard curriculum. I should point out Einstein was a very well-rounded man. He was a fierce champion of scientists learning the humanities and liberal arts. He said that was necessary to be a well-rounded scientist. He played the violin throughout his life quite well, and he was always reading about arts, humanities, and related fields. He said they made him a better scientific thinker, and I'm inclined to agree with that advice. Now, Einstein ended up fleeing Germany at the age of 15. He pled medical problems, but in reality, he was wanting to get out of military service. German law at the time required every young German man of the age of 15 or greater to register for military service. And Einstein, who was a pacifist like Tesla, wanted nothing to do with it. So he fled to Switzerland and renounced his German citizenship. He lived in Switzerland for several years, ended up attending the Swiss Federal Institute of Technology, getting his degree in, he enrolled in 1896, got his degree in 1900 in physics. But he was not recommended for doctoral work. His professors said that although he was brilliant, he was a lazy dog and would never amount to anything useful. So, he was not recommended for an academic posting nor for continued doctoral study. In 1902, he became a patent clerk in Switzerland, using his knowledge of engineering and physics to evaluate technologies being submitted for patent proposals. But while he was at the patent office, Einstein pursued other projects. He was always working on his own researches in the background. And a lot of times at his desk at the patent office, he was really hiding a notebook with his own physics calculations underneath whatever proposal he was supposed to be evaluating at the time. Einstein did not keep up well with the scientific literature of the day. He worked out most of what he was doing from first principles based on his previous learning, which makes his discoveries all the more remarkable. As Einstein was doing his personal physics research, he came to the conclusion that Maxwell's electrical equations for electromagnetism cannot be reconciled with Newtonian mechanics, at least not in the absolutist view that Newtonian physics had previously offered. And he sets himself to solving this mathematical conundrum. In 1905, Einstein had a good year. That year, he submitted 4 papers to various journals. He called it later his annum mirabilis, his miraculous year. Any one of the 4 papers he submitted that year would have been sufficient to get him mentioned in this class. And he did them all at the same time. The 4 papers Einstein submitted in 1905 to various journals and institutions. Firstly, one called On a Heuristic Viewpoint Concerning the Production and Transformation of Light. This was a paper on what today we call the photoelectric effect. Einstein noted that light energy can be absorbed or emitted only in the form of small, discrete packets of energy, which he dubbed quanta. From that term, we get the term quantum physics, although Einstein himself did not really develop that principle. His ideas on quanta of light were not widely accepted until 1923, when people like Niels Bohr were doing work in quantum mechanics demonstrating the efficacy of Einstein's ideas. Nonetheless, his discovery of quanta of light served as the basis for wave-particle duality and for all the quantum physics that came later. Even though Einstein himself rejected a lot of the principles of quantum physics, he argued good-naturedly with Niels Bohr about it throughout his career, famously described it, as he put it, as spooky action at a distance. Now, that was just the first of the papers that he became really famous for. The second one he published that same year was on the motion required by the molecular kinetic theory of heat of small particles suspended in a stationary liquid. Einstein had many gifts. Succinct titles was not one of them. Now, that paper explains a phenomenon known as Brownian motion, which some of you might be familiar with if you've ever worked with a microscope. Brownian motion is the jiggling of small particles suspended in fluids that we sometimes observe underneath microscopes. Now, nobody had really explained Brownian motion up until that time, but Einstein demonstrated empirically that what was happening in Brownian motion is that the microscopic particles in question were being collided with by atoms that were even smaller but were not visible to the microscope itself. That paper proved the validity of statistical mechanics as a field of inquiry, but more importantly, it finally provided empirical proof of the existence of atoms, something that had been lacking since way back when Democritus first proposed the idea 2,400 years earlier. So Einstein's paper was pretty important for physics as a whole. Should point out about that one, story about that paper. That is the paper that got Einstein his doctorates. Now, in those days, the University of Zurich would accept unsolicited doctoral dissertations from people who were not attending there, and if they judged them to be fit, they would award them a PhD. Now, Einstein submitted his paper on Brownian motion as his doctoral dissertation. The university got back to him and said, "This is amazing, this is extraordinary, this will change the face of physics. You have finally demonstrated a vital idea for both physics and chemistry. We cannot award you your doctorate because your paper is too short." Einstein resubmitted the paper a week later with an extra sentence added on talking about how the discovery was going to revolutionize physics, chemistry, etc. They got the point and gave him his doctorate. Third paper that Einstein published that year was entitled On the Electrodynamics of Moving Bodies. This was his attempt to reconcile Maxwell's equations with Newtonian mechanics, and he found that the only way he could do that was with the demonstration that there is no universal absolute frame of reference, that contrary to Newtonian mechanics, that space, time, and motion are all relative to the observer, with the only constant in every frame of reference being the speed of light. That, of course, is the basis of what is now called the special theory of relativity. Einstein's special theory of relativity has been vital for everything from satellite communications to our understanding of space travel and nuclear energy, and it is one of the foundational principles of physics as we know it today. And finally, the fourth paper he published that year was entitled, Does the Inertia of a Body Depend Upon Its Energy Contents? That paper demonstrates the relationship between matter and energy. It shows that an atomic nucleus is essentially a stored form of energy, that it is potential energy stored within its mass, and that if atomic nuclei are broken down, they will release a titanic amount of energy, specifically an amount of energy equal to the mass of the particle times the speed of light squared. In other words, the very famous equation E equals mc squared. That principle lies at the base of all nuclear science, demonstrates that matter and energy are in fact aspects of the same phenomenon. After 1905, needless to say, Einstein started getting some attention. These discoveries put him on the map, and he was offered teaching positions all over the place, and ended up accepting a professorship at the University of Berlin. Now, Einstein, over the next several years, did a lot of pretty cool stuff. In 1909, he introduced the concept of the photon as the quantum unit of light. In 1910, he wrote a paper explaining why the sky is blue, demonstrating the scattering of wavelengths in the upper atmosphere. And finally, in 1915, he finished the work he had begun with the special theory of relativity in publishing his general theory of relativity. General theory of relativity introduced the concept of a fourth dimension of curved spacetime, showing that essentially curvature in space around heavy bodies was responsible for the force of gravitation, and that time was a physical dimension. This explained, among other things, gravitational redshift, the ability of gravity to affect light, and a very important implication of Einstein's work here, the fact that the universe is expanding. General theory of relativity, along with the special theory, are some of the bedrock of modern physics, and for the first time in history, demonstrated how gravity might work, solving a problem that Newton himself had failed to solve 250 years earlier. So Einstein's work here is opening up all kinds of new doors. Incidentally, two things about the general theory of relativity. It was not widely accepted at first. It was actually not widely accepted until into the 1920s, whenever finally other discoveries began verifying its claims. The general theory of relativity predicted the existence of gravity waves as being a phenomenon that would demonstrate how gravitation was being affected by it. Gravity waves were finally proven to exist in 2018, putting in the last missing piece of that puzzle. And finally, the general theory of relativity. Remember how I said it predicts the expansion of space? Einstein himself did not believe in that. He thought the expansion of space was a ridiculous idea. And therefore, he put a mathematical fudge factor of sorts into his equation that he called the cosmological constant to sort of even out the forces so that the universe didn't need to expand in accordance with the predictions. Later, when the work of Edwin Hubble, the astronomer, demonstrated that the universe was in fact expanding, Einstein backed down, admitted he was wrong. He called the cosmological constant the biggest blunder of his career. Although I should point out that the mathematics behind it are being used today by some physicists investigating the phenomena of dark matter and dark energy. So maybe he was onto something there, but the universe is in fact expanding. So He's continuing with all this. General relativity is going to make him world famous. He's going to receive a Nobel Prize in Physics in 1921 for his discovery of the photoelectric effect. And he's going to become quite a prominent figure in the physics of the age. Now, if you know your 20th century history, that you know that throughout the 1920s, Germany was in a little bit of a pickle. It was shattered after World War I and was coming back together around fascist and authoritarian views, particularly at the hands of a young political radical by the name of Adolf Hitler. Now, as time is going on here, it's getting less and less comfortable to be a Jew in Germany, and Einstein is a Jew. He is more than that, a Zionist. He is an advocate of a Jewish homeland. Not a popular idea in 1920s Germany. In 1932, Einstein travels to the United States, and he never comes home. He came here for scientific visits and giving some lectures, only to find that 3 months later, Hitler passed a law banning any Jew who had not served in World War I from holding a job in Germany, a move often regarded as the beginning of the Holocaust. Einstein never returned home, stayed in the United States for the rest of his life, got himself a position teaching at Princeton University, and there he remained as an instructor and physics researcher until his death. Einstein spent the latter years of his life working largely on unified field theory, the idea of trying to find a way to mathematically unify all of the basic forces of nature. He never completed it within his lifetime, but his work with unified field theory now serves as the basis of the Standard Model in physics. The Standard Model, of course, being the unified explanation of particles and energies, of which gravitational waves are finally filling in a big missing piece, and perhaps enabling modern physicists to arrive at the unified field theory that Einstein himself never did. Now, he becomes a U.S. citizen in 1940. In 1939, just prior to that, he wrote a letter to President Franklin Delano Roosevelt, warning President Roosevelt against the possibility of a German nuclear weapon, that Nazi Germany might endeavor to harness the power of the atom to build a bomb of titanic proportions. Einstein intended this as a warning. FDR said, uh-oh, we better get underway with our own. And on the basis of Einstein's letter, he initiated the Manhattan Project, the research effort to create a nuclear weapon. Einstein was involved in the early days of the Manhattan Project, but then ceased to be involved whenever the government became clearly aware of the fact that as a pacifist, he had no interest in making a nuclear weapon, and ultimately pulled him from the project. Einstein was kind of okay with this because he didn't think it was a good thing to be doing. He blamed himself for the nuclear bomb and its devastation for the rest of his life. In his latter years, Einstein actually became a very colorful figure in areas outside of physics. He was an outspoken advocate of denuclearization, civil rights, and the desegregation of schools. He was also an outspoken advocate for the state of Israel. In fact, when Israel came together as a nation in 1948, Einstein was offered the position of its first president, which he turned down because he said that as a man of science, he did not feel he was qualified to be a politician. But his political views and his advocacy for progressive causes actually got him accused of socialist leanings here in the United States. And in point of fact, reading Einstein's personal writings, that's probably 100% accurate. He was absolutely a socialist, but not a communist, as was often perceived at the time. Einstein ultimately had a brain hemorrhage in 1955 and died quietly in his bed. His brain was left to science in order to do autopsies on it and find out if there was anything anything cool about his brain that made it especially unique as compared to other people's. And I just said brain aneurysm, my bad. It was an aortic aneurysm that killed him. Dissections of Einstein's brain that were done in 1999 incidentally revealed, among other things, it's slightly smaller than the average human male brain. And those of you who are bio folks know very well that there's not a direct correlation between brain size and intelligence. But it was found that he had a lack of a lateral sulcus in the operculum of the inferior frontal gyrus, which for those of you who are not anatomy folks, means that he had more communication between the frontal and parietal lobes of his brain, which may have assisted him with mathematical thought visuospatial cognition and imagery of movements. So he may have had a biological advantage helping him to process this high and rarefied mathematical information that other people had not mastered. All right, so Einstein is laying the basics of a lot of physics down, but he's talking about a lot of things that are nuclear and a lot of things involving radiation in the atom. Much of his work could not have been done without the work of a rather remarkable pair of scientists, including arguably the most prominent woman scientist of the 20th century, and one of the first women scientists to come to any real notes. I am talking, of course, about Marie Curie and her husband, Pierre Curie. Marie was born in 1867, died in 1934. Pierre was born in 1859, died in 1906. We're a couple days off his death date, April 19th. Now, Pierre was French, Marie was Polish, and that particular pair of chemists and physicists were pioneers in the science of radioactivity. Marie Curie, a rather remarkable person in many respects. She was the first woman to receive a Nobel Prize, was the first person, male or female, to receive 2 Nobel Prizes, and to date, she is the only person to have received both the chemistry and physics Nobel Prizes. Now, Marie Curie was born under a different name. Her birth name was Maria Sklodowska, Sklodowska. You'll see it's spelled a couple different ways in the translation from Polish, but Maria Sklodowska was her birth name. Her parents were school teachers in the Polish capital of Warsaw. She grew up in a Poland that was controlled by Russia. She was quite bright as a young woman. She would always be the one who was asked to answer questions whenever the Russian inspectors would come to the Polish school to make sure that they were all being taught proper Russian, because she spoke fluent Russian, even as a child. Now, she was quite gifted academically. Her parents encouraged her learning. They firmly believed that women and men had equal intellectual capabilities, and they encouraged her interests in math and science. Marie graduated high school at the age of 15, but unfortunately, Russian law at the time forbade native Poles from attending universities. So, she went to an illegal underground college, sometimes called the Floating University or the Flying University, which offered Poles classes they could not take at legal universities. The unfortunate thing about an illegal underground college is it cannot grant you a legitimate degree. As a result, she knew that if she wanted to carry on her scientific ambitions, it was going to have to be somewhere else. So she made an agreement with her sister Ava that the two of them would travel to France, and that they made a partnership where Ava would study medicine while Marie worked to support her and put her through school, and then Ava would work to support Marie while she studied the sciences. So Marie worked as a governess for a while, supporting her sister's medical education. France was one of the few countries at the time that allowed women to get MDs. And then her sister paid for her to go through college. She studied mathematics, physics, and chemistry at the University of Paris, where she made quite a stir as being one of the only women at the university at the time. In fact, she was often forced to work at separate lab benches apart from everyone else because it was feared that she would be a distraction to male students. Ultimately, despite the prejudice that she suffered, she persevered and was awarded her doctorate in 1903, becoming only the second woman in Europe to receive a PhD. Her doctoral professor was Henri Becquerel, Henri Becquerel, Becquerel. Henri Becquerel was a pioneer in the science of radiation, and with his students, Marie and Pierre, he began working on the fact that certain kinds of materials, namely certain ores of uranium, seemed to emit energy at all times, no matter what else was happening. Marie and Pierre largely cracked the puzzle and determined that certain elements were unstable and emitted energy in the form of radiation, the phenomenon which Marie would name radioactivity. It was that discovery that granted Becquerel, Marie, and Pierre the Nobel Prize in Physics in 1903. The Nobel Committee did not want to include Marie on the prize, saying that she was just an assistant, and Pierre insisted that she be included, saying, if anything, she was the brains of the operation. Now, Pierre Curie was a man she had met while studying under Becquerel. The two of them married and ended up having 3 children. 2 of their daughters went on to become Nobel Prize laureates in the sciences on their own right. Now, as they're studying their radioactivity, they realize not all uranium ores are equally radioactive. Some are more active than others. And they surmise that there must be another radioactive material, some other elements present in uranium ore, which is giving off a different level of radiation. So Marie and Pierre undertake to isolate whatever that substance is that is more radioactive. They are forced to work outside the main university laboratories, again, because Marie as a woman is seen as a distraction. They are doing their work in a small, unventilated and unheated shed on a corner of the university property, where they are patiently and carefully hand processing tons of uranium ore in an unventilated space without anybody realizing at the time exactly how dangerous a thing this was to do. Their work paid off. They ended up isolating not 1, but 2 elements more radioactive than uranium. One of them they name polonium for Marie's native Poland, and the other is named radium, more than 1 million times more radioactive than uranium. Now, you're probably thinking to yourself, this is not going to go well. And you're absolutely right. Because they're being exposed to vast amounts of radiation and not aware of the danger. Marie kept a vial of radium in her desk drawer because she said the pretty blue light that it emitted soothed her when she was feeling stressed. Her husband would take that vial of radium and stick it in his breast pocket and take it to parties to show off the amazing thing his wife had discovered. In 1906, Pierre was hit by a carriage. His bones were weakened from heavy radiation exposure, and he died instantly, leaving Marie a widowed mother of 3. She assumed his position at the Sorbonne, the Academy for Sciences within the University of Paris, held that position for much of the rest of her life, and demonstrated quite conclusively to the people who had wondered if her husband was doing all the cool work that, in point of fact, she was the one who was really driving the science. Not to say Pierre Curie was any slouch, but at the end of the day, Marie was really the one who was doing the amazing stuff here. She was a figure of controversy. She was accused of an affair with another professor, which may or may not have been true, but she continued plugging away with her scientific work, in particular, promoting the usage of radiation for a wide range of applied purposes. She declined to patent the radium refining process to make it easier for other countries to get it for research. She went on to build a mobile radiography unit, which in World War I, she and her daughter Irene took to the front lines of the Western Front in France and demonstrated its use personally to combat medics. The use of X-rays in the field would end up proving invaluable to saving the lives of countless thousands of soldiers and would, of course, revolutionize medicine as we know it. Sadly, Marie, too, was going to suffer from exposure to the products of her research. In 1934, she would die of aplastic anemia and leukemia, almost certainly a result of her radiation exposure. Prior to that, in 1911, she won the Nobel Prize in Chemistry for the discovery of radium and polonium. Her husband was not included in that prize because he was dead by then, and the Nobel Committee does not award posthumous prizes, so she is the sole holder of that prize. And again, the only person, male or female, to get both the chemistry and physics prizes. All right. So I think Marie Curie's story is well worth the telling, and just as a postscript to it, her husband and her notebooks and lab equipment are to this day kept in a lead-lined vault at the French Academy of Sciences, because 120 years gone, they are still too radioactive to safely handle. Made a big sacrifice for the knowledge that she gave to mankind. All right, now let's get this into nuclear physics, right? We're definitely moving in that direction. We're gradually gaining awareness that the atom is more complex than we thought, And because it is emitting energy, and Einstein has showed us matter energy equivalency. There we go. It's clear that maybe the atom is not the smallest of all particles. And so we're starting to explore that branch of nuclear physics and chemistry to a much deeper level. Start that discussion with a fellow by the name of Sir Joseph John Thomson, J.J. Thomson. You probably heard that name. Thomson was born in 1856, died in 1940. British-born Scottish physicist, Cavendish Professor of Physics at the University of Cambridge, worked at the famous Cavendish Laboratory. Thomson worked with cathode ray tubes, and he and his assistant, Margaret Todd, discovered that cathode rays being sent through a tube of gases could be bent and deflected by electromagnetic force. This led to the conclusion in 1907 that what they were looking at, this electric force, was actually a stream of discrete negatively charged bodies, or corpuscles as they call them, which are now known as electrons, and for which Thomson would win a Nobel Prize for their discovery. Building on this, Thomson developed the so-called plum pudding model of the atom, suggesting that the atom was basically a solid mass with electrons embedded within it, like raisins stuck into an English plum pudding. He thought the electrons were within the atom. A few years later, in 1913, he and Todd are experimenting with cathode rays shined through tubes of inert neon. Now they found, of course, neon being an inert gas does not react in this situation, but they did find that they observed two distinct parabolas of deflection, that not all the neon was deflecting the cathode rays in the same way. This led them to the conclusion that there is, in fact, more than one kind of neon, the discovery of what we now know as isotopes. In the course of the research on this, Thomson also invented a device that many of you have used in lab, the mass spectrometer. Now, Thomson had a lot of very famous students, but arguably the most brilliant of those, and the most well-known, another guy you might have heard of in your chemistry classes somewhere, was a fellow by the name of Ernest Rutherford. Rutherford was born in 1871, died in 1937. He was a native of New Zealand, Scottish by ethnicity, ended up succeeding Thomson as the Cavendish Professor at Cambridge. Studied under Thomson, later did postdoctoral work at McGill University in Montreal from 1900 to 1903. There, Rutherford and one of his students, a rather famous nuclear scientist named Frederick Soddy, who later worked on the Manhattan Project, together they showed that radioactivity results from the spontaneous decay of unstable atoms. This led them to the discovery of the concept of the half-life, as well as the three basic forms of radiation, alpha, beta, and gamma radiation, for which Rutherford would win a Nobel Prize in 1908, and which would form the foundation of radiometric dating technologies, like carbon dating. More on that in a little while. In 1909, Rutherford is carrying out experiments firing alpha particles, which you might know from your physics class are 2 protons plus 2 neutrons, basically helium nuclei, firing a stream of alpha particles at a sheet of gold foil. He's being assisted in this by 2 other very famous physicists, Ernst Marsden and Hans Geiger of Geiger counter fame, both of whom are also going to become Nobel Prize winners eventually. Now, as they're firing these alpha particles, that sheet of gold foil, most of them are passing right through it, but some are deflected back. Rutherford and his students conclude that they must be repelled by something with the same charge as them. An alpha particle is a positively charged particle, and Rutherford concludes there must be a positively charged part of the atom that is reflecting those alpha particles, since we know by now that electrons are negative. This leads him to the conclusion that the structure of the atom must be a little different than what people thought. And he proposes a new model of the atom. The Rutherford model of the atom is the one you're all familiar with. Clump of particles, little bands going around the outside. He hypothesizes a positively charged nucleus surrounded by orbiting electrons. In 1909, by continuing further experiments to learn the properties of the nucleus. He bombards atomic nuclei with streams of charged particles, fires a stream of protons, as we now know them, and he's going to name them the proton after William Prout, at nuclei of nitrogen atoms. He discovers he can make them stick and transform a nitrogen atom into an oxygen atom, moving it up one spot in the periodic table. Rutherford had achieved the alchemist's dream. He had converted one element into another. He actually hesitated to publish it first because he's like, they're going to call me a damned alchemist if I publish this. Ernst Marsden ultimately had to persuade him to come forward with his discoveries because otherwise he was afraid he would have been laughed out of chemistry. He discovered if you actually bombard a nitrogen nucleus with alpha particles, it will become an atom of oxygen and it will emit a hydrogen nucleus, a single proton, as a byproduct. And he comes up with the name proton, naming it after William Prout. In 1921, he suggests that the nucleus cannot be all positive particles or it would be self-repelling, and hypothesizes the existence of the neutron. That will ultimately be proven in 1932 by another student of his, a fellow by the name of James Chadwick. Rutherford's going to get a lot of credit for his accomplishments. He's actually going to be named a Baron, the first Baron Rutherford of Nelson, in 1931 in honor of his scientific achievements. Sadly, he does not get to enjoy his title for very long. In 1936, he has a hernia operation and dies of complications 6 months later. Now, Rutherford had a lot of very famous pupils, but arguably the most famous of them, and a guy who's going to start to get us into two of the most interesting stories in 20th century science, is going to be a Danish physicist by the name of Niels Henrik David Bohr, B-O-H-R. And the name Niels, by the way, N-I-E-L-S. Niels Bohr, one of the great names of 20th century science. You've probably heard of him. Born in 1885, died in 1962. Pioneer in both atomic structure and, of course, in quantum mechanics. Bohr came from a half Jewish and half Lutheran family and studied physics under both Thomson and Rutherford. Now, as he's working with both of them, he's seeing their respective models of the atom, the Thomson plum pudding model, and then Rutherford's more elaborate model with a central nucleus and orbiting electrons. But Bohr was troubled by the Rutherford model because he said, what is keeping the electrons from falling into the nucleus? In 1913, after considerable observation and calculation, he publishes the model of the atom that you probably learned in your chemistry class today. Well, maybe not today exactly, but modern times, the Bohr model of the atom. The Bohr model of the atom, of course, suggests that electrons travel in specific defined pathways around the nucleus called orbitals. That those orbitals are going to exist at specified distances from the nucleus, which are the only places where those electrons can exist. That is where their waveform is stable. And that enables them to remain in stable orbital positions at a specified energy level. He realizes that the further out from the nucleus you get, the more energy an electron has, and determines that if you add energy to an atom, you will cause the electrons to become excited. Electrons in lower level orbitals will jump to higher level ones, displacing higher ones to the lower level. And at that point, when a higher level electron is displaced to a lower level, it emits a quantum of energy, specifically a photon of light. This, by the way, is what's happening in the phenomenon we call fluorescence. His model suggests several important things, but one of the most notable of them is that the electrons that change from one level to the next, when they are jumping in that way and emitting a quantum of energy, they go from one orbital of the electron to the next without passing through the intervening space. They simply cease to exist at one orbital and resume existing at the next one, a phenomenon which Bohr names the quantum jump. And all of this is going to become the basis for his most famous contribution to science, the discipline known as quantum mechanics. Bohr is going to discover the valence properties of atoms. He's going to discover that electron orbitals account for the periodicity of atoms and why they have similar properties across the periodic table. He will also discover how valence electrons are involved in chemical bonding and demonstrate how valence electrons form covalent and ionic bonds. He gets a Nobel Prize for that in 1922. Now, throughout the 1920s, Bohr begins building on his principles of quantum mechanics. He's not doing this alone. He's partnering up with a couple of other very famous physicists in this matter, a German by the name of Wolfgang Pauli, P-A-U-L-I, noted for the Pauli exclusion principle that says that no two electrons can occupy the same place at the same time. And of course, his very famous student, Werner Heisenberg, of Heisenberg's uncertainty principle fame. We'll talk more about him specifically in a few minutes. Throughout the 20s, Bohr and his colleagues begin developing the fundamental principles of quantum mechanics. Complementarity, the idea that a particle can be analyzed as having several contradictory properties at the same time, wave-particle duality, for example, and the idea that observation is critical to behavior of particles, the notion that at the fundamental subatomic level, the Newtonian laws of mechanics break down. Bohr argues very good-naturedly about Albert Einstein with this. Einstein, of course, calls this spooky action at a distance. And ultimately, Bohr is kind of the grandfather of quantum mechanics here. He and others put together a famous formulation known as the Copenhagen interpretation, which is the basis of the theoretical foundations of quantum mechanics, even to the present day. Now, Bohr is doing some amazing things. And it is arguable that at this point in time, and going into the 1930s, Niels Bohr knows more about atomic structure than anyone else alive. Now, we're moving into the 1930s, and of course we are moving more and more into a time of war. The drums of war are beating across Europe. Nazi Germany is getting more and more ambitious and starting to reach out into the surrounding territories. Battle lines are being drawn, and it is becoming abundantly clear to everybody two things. One, there's a big war coming. World War II is in the offing. Everybody sees it coming long before it begins. And two, the key to that war is going to be who has the better tech. Science will be the key to winning or losing World War II. Now, Bohr is courted by the Allies. Denmark is not in with the Nazis, and Bohr is approached by Allied scientists who want to get him on board with their research projects, but he's not committed as yet. Now, Bohr, as I mentioned, has a famous pupil by the name of Werner Heisenberg. Let's talk a little bit about Heisenberg for a minute. Heisenberg was born in 1901, died in 1976, pretty recently. Major figure in quantum mechanics. He was a student of Niels Bohr, collaborated with him throughout their professional lives. In 1925, Heisenberg formulated matrix mechanics, which is a very important part of quantum mechanics, and the math involved with it allows us to mathematically explain quantum jumps. And he begins realizing that electrons do not seem to have one firm orbital pathway. They seem to move around in their orbital paths. This leads him in 1927 to introduce the idea for which he is most famous, Heisenberg's uncertainty principle. And by the way, Heisenberg, Heisenberg. Heisenberg's uncertainty principle, you probably already know, states that the act of observation changes the object being observed. That it is not possible to know the position and the velocity of an electron or another subatomic particle at the same time, because measuring one will actually change the other one. Therefore, he says, quantum behavior of subatomic particles must be understood not in terms of exact positions and velocities, but in terms of probabilities, of likely locations. And he imagines the movement of electrons as a cloud-like movements in which they remain at a constant distance from the nucleus, but have a very irregular orbital path, constantly shifting and changing. Heisenberg's uncertainty principle, the idea that that which is observing changes the thing being observed, is not only vital to quantum mechanics, but also it's a very important principle in philosophy. With Niels Bohr, Heisenberg and Wolfgang Pauli formulate the Copenhagen interpretation of quantum mechanics in 1928, it's the basis of that modern science, asserting that classical Newtonian physics cannot meaningfully account for the behavior of particles at what they call the quantum level, the subatomic consideration, and therefore that you must look at these things with inherent mathematical uncertainty. In the 1930s, Heisenberg built on Rutherford's research, proposing the proton-neutron model of the atomic nucleus. He's becoming quite a prominent physicist in Germany in his own rights, but he gets in trouble for teaching the works of Albert Einstein. Einstein is viewed as a fugitive and a treasonous Jew after he flees Germany, and his works are banned in German physics departments, which, needless to say, kind of makes it a little bit hard to learn about certain aspects of physics. Heisenberg insists you need Einstein to understand it. He gets in trouble for that on more than one occasion. But Germany likes him. Germany knows that Heisenberg is needed. His knowledge is perhaps bar none to any other German scientist about nuclear power. And he's recruited by the Nazi government for the study of nuclear phenomena. Now here's where the story re-intersects with that of Niels Bohr. Because Heisenberg is working for the Nazis. Bohr is being courted by the Allies. The two men are still friends. They're still exchanging information on their relative quantum research and so forth. But as the drum beats of war sound louder and louder, both sides begin putting pressure on them, saying, hey, do not do this anymore. Stop talking to a potential enemy. And they are forced to put distance. Now, Heisenberg was loyal to Germany. He was not loyal to the Nazi Party. He did not like the Nazis one bit. But he did get heavily involved in German nuclear research, including military nuclear research. Now, one day, the end of September of 1941, Bohr gets an unexpected visitor. Heisenberg shows up at his home in Copenhagen, having snuck out of Germany. The two men spend 5 days together between the end of September and beginning of October 1941, catching up on old times, talking about their respective research, and of course, talking about what's coming. And at the end of that visit, Heisenberg proposes a deal. And he says to Bohr, look, you and I know more about atomic structure than anyone else alive. I know your side wants you to help build a bomb. You know my side wants me to help build a bomb. Let's make sure that nobody gets the bomb. Let's you and me both agree that we are not going to contribute our knowledge to forming atomic weapons. Let's keep that weapon from ever existing. We can do this. Bohr gets cold feet. He doesn't know if he can trust his old friend anymore. He is afraid that Heisenberg has been seduced by Hitler. And he says, no, sorry, I cannot accept that deal. Heisenberg says to him, okay, I'm going to go home now. Get out while you can. Bohr takes the hint and gets out. Flees to the United States. 2 weeks after he flees Copenhagen, his home is raided by the Nazis. And Bohr presents himself to Franklin Delano Roosevelt and says, okay, I'm ready to get on board. Sign me up. Thus, Niels Bohr becomes one of the chief scientists involved in the Manhattan Project. You've all heard of the Manhattan Project. Ran from 1941 to 1945, the extensive research effort to develop a nuclear weapon. Named because it first began in hidden laboratories underneath a set of baseball bleachers in the city of Manhattan, New York. The project then later moved to the deserts of New Mexico, to a secret research community called Los Alamos, in which mathematicians, scientists, and engineers gathered, handpicked by the U.S. government in secret from throughout the Allied nations, to come together with the collective goal of building a nuclear weapon. The project would cost the equivalent of $27 billion in terms of modern money. It was the single largest scientific investment in a single project that had ever been made up at that point in time. Now, the Manhattan Project was a who's who of great names in physics, not only Bohr, but a wide number of other brilliant individuals. The project was, of course, headed up by the famous American quantum physicist J. Robert Oppenheimer, born in 1904, coming up on his birthday, April 22nd, died in 1967. Of course, Enrico Fermi, the Italian physicist who produced the first self-sustaining nuclear reaction in 1942. And the rather famous and eccentric American physicist Richard Feynman, Feynman, who became quite famous for his very plain-spoken and easy way of explaining scientific phenomena to non-scientists, his mingling of the sciences and liberal arts, and the incredible insights about quantum mechanics that he got while he was on heavy drugs. Now, these are among many of the names that are going to be involved in the Manhattan Project. And these men, along with others who I'm not going to tell the story of because that story would take up even more than we've already talked about thus far, are all gathered together at this secret community in Los Alamos, New Mexico, throwing their knowledge together in a race against time to build a nuclear weapon before Hitler. They work feverishly for several years. They make some amazing discoveries about the nature of nuclear energy along the way. And in July of 1945, July 14th of 1945, I meant to say, July 14th, 1945, the men are looking at what they think, if it works, is going to be a functional atomic bomb. FDR had died a few months prior of a brain hemorrhage, but World War II is still going on. And Harry Truman believes that we need this weapon to end the war in Japan and the war in the Pacific. And so, Manhattan Project says, we got your bomb. We don't know what it's going to do. We don't know if it's going to work as it's supposed to work. We don't know what kind of energy it's going to release. One of the equation simulations that Feynman ran suggested that this nuclear reaction would never end once it began, and that it would consume the entire world. But Truman was desperate for the victory, and he said, all right, I need you all to test this thing. July 14th, 1945. The bomb named Trinity is taken far out into the desert to the site of Alamogordo. And early in the morning, while the scientists are far, far back, they push the button. You all know what happened. The world changed that day. The mushroom cloud rose up over the deserts. The beginning of the nuclear age and the Anthropocene epoch of geology. Bohr was standing beside Oppenheimer when the bomb went off as they watched. Oppenheimer was a student of Eastern mysticism, of Hinduism and Buddhism. And Bohr said that as they watched the explosion, Oppenheimer quoted from the Hindu holy book, the Bhagavad Gita. And what he said was this: if the radiance of 1,000 suns were to burst at once into the sky, that would be like the splendor of the mighty one. I have become death, destroyer of worlds. They knew what they had made. The first atomic bomb, named Little Boy, was dropped by a plane called the Enola Gay on the city of Hiroshima, Japan on August 6th, 1945. 3 days later, a second bomb called Fat Man was dropped on the city of Nagasaki on August 9th. Japan surrendered within days, ending World War II. Now, you can argue back and forth forever, and historians of war and of science will argue back and forth forever about whether or not it was necessary to drop the bomb to end the war. No doubt many of you have been told in other history classes or in documentaries or in other things that a land invasion of Japan to end the war would have cost 1 million American lives, and that arguably, therefore, dropping the atomic bomb was saving lives. I'm here to tell you, whatever you think about the morality or whatever you think about the necessity of dropping an atomic weapon on Japan, a few things you need to know about that. One, that figure of 1 million lives lost in that invasion was completely made up. Harry Truman knew he needed to sell the American public on this and why such a devastating weapon was necessary. And when his generals came to him with estimates of how costly that invasion would be, the numbers were far too low. He said, make it 1 million. That'll sell. And 2, we dropped 2 bombs on Japan, Hiroshima, Nagasaki. Thousands of people were vaporized in an instant. People further back had their eyes melt in their sockets. Some folk were destroyed so rapidly that their shadows were burned into walls. You can still see them in Hiroshima and Nagasaki today. After the Hiroshima bomb was dropped, Japan was already drafting articles of surrender before the Nagasaki bomb. We knew. Our spies in Japan knew. The Nagasaki bomb was not dropped to make Japan surrender. The Nagasaki bomb was dropped to impress Russia. Because we knew very well that the fragile alliance between communist Russia under Joseph Stalin and democratic America was not going to last beyond World War II. The battle lines were already being drawn for the Cold War. And we needed to have a posture. This was a way of saying to Stalin, hey, you saw that thing that we did in Hiroshima? We can do it again. Back off. The irony of all that, I think in a lot of respects, is that the Manhattan Project created exactly enough fissile material for 3 bombs. Trinity, Little Boy, and Fat Man. And at that point, no, we didn't have another one. Conclusive casualty figures for how many people perished in those explosions, not only because we don't know how many people died when it happened, but we don't have a good count of how many people died in the days, months, years, and even decades to come of the consequences of massive radiation exposure. A conservative estimate suggests that the Hiroshima bomb killed 135,000 people, the Nagasaki bomb 75,000. And whatever else you think about the morality of the atomic bombing, the Nagasaki bomb was completely unnecessary to end the war in the Pacific. 75,000 people died in Nagasaki, so America could show off to Russia. You can take that to the bank. What about Heisenberg? He and Bohr never fully reconciled. They never fully got around to being good friends again. Their relationship was always chilly from that point onward. They both told slightly different versions of the story of what happened at that fateful meeting in October and September of 1941. But as far as we can tell, Heisenberg was true to his word. Throughout the war, he continually diverted resources away from research into atomic weaponry and toward research on atomic energy. It is highly likely that Werner Heisenberg, through his efforts in the background, prevented the Nazis from developing a nuclear bomb before the war in Europe could end. And as such, that was very likely a significant salvation for a significant number of people. In the years following World War II, virtually everyone involved in the Manhattan Project became involved in outspoken efforts for the peaceful use of atomic weapons. Bohr spent the rest of his life advocating for the peaceful use of nuclear power. Oppenheimer worked for international controls on nuclear weaponry, and in fact was so ardent in his outspoken cry for disarmament that he lost his security clearances over the accusations of communist leanings by Joseph McCarthy, and thereafter was not able to do research for the United States government. Enrico Fermi went on to do research on subatomic particles such as muons and pions. Nearly everybody involved felt the bomb had been a mistake. Nearly everybody involved died ultimately of severe multiple organ cancers. 2 last little stories I want to tell about the Manhattan Project here. One of them involves Richard Feynman. Richard Feynman is one of the few members of the project that remained involved in weapon research after the war, and he helped the United States in the subsequent years to build the first hydrogen bomb. A bomb so powerful that you had to basically set off a standard fission nuclear bomb in order to get enough energy to make it go. Feynman was involved in research with this, and he was always a quirky figure, and he was well known for his mathematical genius, his ability to do calculations in his head faster than most people could do them with a slide rule, which was the standard pre-calculator device at the time. Now, what I'm about to tell you is a piece of folklore. It is not anything I found recorded in any formal scientific history text. It was told to me by my father, who was a nuclear chemist, that while they were working on the hydrogen bomb, Feynman had a bet going with other scientists involved that he could calculate the temperature radiating out from the point of explosion to a very high degree of precision. His fellow scientists said, you can't get it that good. So Feynman made a bet with them. They were testing a hydrogen bomb. Before the test, Feynman goes to a specified point that he has calculated out in the radius away from where the bomb is being detonated. He takes a parabolic reflector, sets it at that spot, balances a cigarette in it. Then gets way, 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 way back. They detonate the bomb. And when the dust settles, Feynman walks out across the radiation-laden field, picks up the cigarettes, which is smoldering at the very tip exactly where he said it would, and takes a puff, thus winning that bet, becoming the only person in human history to light a cigarette with an atomic bomb. Feynman died of abdominal cancer in 1988. And the last story about the Manhattan Project that is worth mentioning. The United States government feared throughout the entire project that the Russians had a mole on the inside. There was someone who was a Russian spy. In later years, the finger for that supposition has often fallen on the head of the project itself, J. Robert Oppenheimer, who had known communist leanings. Now, we do not doubt that Oppenheimer was a communist. We do not doubt that he spoke out against the use of American nuclear power in the years after the war. And so he was always seen as the best candidate to be the mole on the inside of the project. A few years ago, the Kremlin released some records from World War II area espionage. And among those records, they said, nope, Oppenheimer was not the mole. Yes, there was a mole. Yes, the mole was a highly placed scientist in the project. They showed enough data that proved that somebody on the project was reporting insider information that clearly only the top scientists would have known. And they said, nope, it wasn't Oppenheimer, but we're not telling you who it is. So someone in that elite circle of highfalutin scientists, the great minds of physics involved in the production of the American atomic bomb, was a secret Russian agent. And we still don't know who. Okay, this has run a little bit longer than I normally like these things to go. My 20th century lesson is going to continue. We're not quite done yet, but I think this is a good time to pause and take a little bit of a breather. When we come back, we're going to talk about further fallout, pardon the atomic pun, from World War II. We're going to talk about the development of space technology, of computer technology, and move out into both larger space with the Big Bang and smaller space with the core of the Earth itself. And maybe we'll even say a few things about some DNA. All right, I'll talk to you all in a bit.